Hello everyone. In this video we'll discuss about eddy currents, advantages and disadvantages of eddy currents, and also introduce inductance. So far what we have studied is that if a current is induced in a coil or a rectangular conductor like this, then the current which is induced will have a very well defined path through which it can flow. For example, if you consider a ring here, then the current induced can easily flow through the ring in anticlockwise direction. And here also, in the rectangular conductor, the current will easily flow through this conductor in a clockwise direction. So in both the case, the path is well defined. Now instead of this ring, where the induced current have well defined path to flow, what if we use a bulk conductor metal sheet like this? If this bulk conductor metal sheet is subjected to change in magnetic flux, then also the current will be induced in the metal sheet. Now let us discuss how the current will be induced and how the induced current will flow in the bulk conductive metal sheet. What will be the direction? The current which will be induced in the bulk conductive metal sheet, we call it eddy currents. And why we call it eddy currents? So let us discuss in details. Here in the diagram, a uniform magnetic field is created by placing north pole and south pole of a magnet side by side, and this is a bulk conducting metal sheet which is tied with a thread to a rigid support in such a way that this metal sheet will oscillate like a pendulum of clock in an external magnetic field. So let us discuss what happens when the conductive metal sheet oscillates through the external magnetic field. So from the right, when this conductive metal sheet enters the external magnetic field region here, the magnetic flux linked with the metal sheet will increase, and due to this change in magnetic flux, the current will be induced in the body of the metal sheet. So in this metal sheet, there is no well-defined path for the current to flow, but this current will flow in a very small loops and can be represented as shown in the diagram here. So this is the eddy currents which are flowing in a small loops. The direction of the current is here anti-clockwise. This induced current, which is flowing in a very small loop, resembles the swirling eddies in water. Here, this is the swirling eddies in water. Due to this reason, we call this current, which is induced in the conductive metal sheet, as eddy current. This is the eddy current which is developed when the metal sheet enters the magnetic region. And in the left side, when the conductive metal sheet leaves the magnetic field, the flux linked with it will reduce, and similarly the eddy currents are induced in the conductive metal sheet. But the direction of eddy current here is clockwise, which is opposite to the eddy currents which is developed in the metal sheet when the metal sheet is entering the magnetic region. So from the figure we can see clearly that the direction of the eddy current on entering the magnetic region and on leaving the magnetic region are in opposite direction. So in the left side, the eddy currents will also be generated in a small tiny loops which are flowing in the clockwise direction. Here is another example where the eddy currents are produced when the disc is rotating between the region North Pole and South Pole. This green arrow represents the direction of the external magnetic field, and this black arrow represents the direction of rotation of the disc. And as the region of the disc enters the magnetic field, then here the eddy currents will be produced and will be flowing in the conductive metal sheet in a very small tiny loops. And here this represents the eddy currents which is produced when the part of a metal sheet enters the magnetic field. And this is the eddy current which is produced when the part of the metal disc leaves the magnetic field. The strength of induced eddy current depends on the area for the current to flow. If plain metal plate is used, then the area available for the eddy currents to flow will be large, and strong eddy current is induced in the plain metal sheet. But instead of this plain metal sheet, if we use slotted metal plate where there is a finger-like structure here, then the area available for the eddy currents to flow will be very less. So here is very small area available, and in this case, very feeble eddy currents will be induced. If plain metal plate is used, then strong eddy currents will be produced, and if slotted metal plate is used, then feeble eddy currents will be produced. Whatever we have discussed about eddy currents, let us sum up as follows. Eddy currents are currents that circulate in conductors like swirling eddies in a stream. They are induced by changing magnetic fields and flow in a closed loop perpendicular to the plane of the magnetic field. The magnetic moment due to the eddy currents depends on the area enclosed by the eddy currents, and magnetic moment is given by current into area. Eddy currents are minimized by using conductors in laminated form and also by making rectangular slots in the metal plate. In order to reduce these eddy currents, either we use a conductor in laminated form means layer by layer insulated from each other, or can be used by making rectangular slots in the metal plate. So this is the way to reduce the eddy currents. We have already discussed in details how eddy currents are induced. Now let us discuss how the eddy currents will interact with the external magnetic field. As the conductive metal sheet enters from the right side, it will feel an increase in strength of magnetic field, inducing eddy currents in anti-clockwise direction. These currents produce their own magnetic fields, and according to Lenz's law, the direction will be given by this red arrow, which is in opposite direction to the external magnetic field, which is given by this yellow arrow. These two magnetic fields will interact each other, and they oppose each other because they are in opposite direction. These two magnetic fields, which are in opposite direction, opposes each other and slows down the velocity of conductive metal plate, thus creating a magnetic drag. So the velocity of this metal plate will reduce as it enters the magnetic field. Again, on the left side of the magnet, the sheet will be leaving the magnetic field, and decrease in magnetic field will induce eddy currents in clockwise direction. This current produces their own magnetic field, and according to Lenz's law, the direction will be given by this green arrow, which is in the same direction of the external magnetic field, given by this yellow arrow. Here both are in the same direction. This will attract the external magnet and again slows down the velocity of the conductive metal sheet, thus producing magnetic drag. So here on the left side also, the velocity of the plate will be reduced as same as when it enters the magnet field on the right side. So this damping forces slows down the moving sheet, providing the braking. And this phenomena is called electromagnetic damping. Here we summarize the electromagnetic damping as follows. A damping force is generated when the magnetic field due to eddy currents and external magnetic field interact with each other. This damping force slows down the moving conductive sheet, providing the braking. This phenomena is called electromagnetic damping. The advantage of eddy braking is that it is contactless, so result in no mechanical wear. As we have already seen that there is no contact between the magnet and the conductive metal sheet, So this kind of braking system has advantage which results in no mechanical wear. Now we discuss about the advantage or use of eddy currents. First use is magnetic braking in trains. When the strong electromagnets which are situated above the rails are activated, the eddy currents are developed in the rails. This opposes the motion of the rail. So here, above the rail, there is a strong electromagnet which when activated will produce a very strong magnetic field, and due to the magnetic field, the eddy currents are induced in the rails, and this opposes the motion of the rail. The second use is electromagnetic damping is used in certain galvanometer to bring the moving coil quickly to rest. The third use of the eddy currents is it is used in speedometer, induction motor, and also in the energy meter. Now the disadvantage of eddy currents. It causes undesirable heating and wastage of power in transformers. This transformer are used to either step up the voltage or step down the voltage. So in the transformer also, these eddy currents are induced, and according to the Gauss law of heating, this eddy current will cause undesirable heating of the transformer and results in the wastage of power. In some cases, eddy currents are very useful, and in some cases, the eddy currents are undesirable also. Now we move on to the next topic, and the topic is inductance. We have already studied that the strength of magnetic field produced by the induced current will depend on the strength of the current. And if that magnetic field is linked with another coil, then the magnetic flux linked with that coil will also depend upon the strength of the current. And if that coil has n number of turns, then the flux linked with the closed wound coil having n number of turns is directly proportional to the current. So this statement can be mathematically written as n phi b directly proportional to the current. So here, this proportionality symbol can be replaced by equals to sign and putting a constant, and that constant we call it inductance. So we can say that the constant of proportionality in this relation is called inductance. So this inductance depends on two factors. One is the geometry of the coil and another one is the intrinsic material of the coil. This inductance is a scalar quantity. It has no direction, it has only magnitude. And the SI unit of inductance is Henry. It is represented by capital H. Inductance is of two kinds. One is self-inductance and another one is called mutual inductance. So self-inductance means the phenomena in which an induced EMF is produced by changing the current in the coil itself is called self-inductance. So in self-inductance, only one coil is there and the current is induced in the coil itself by changing the current in the coil. So from the previous relation, n phi b is directly proportional to I. So here this proportionality symbol has been converted into equals to sign and a constant, and this L we call it self-inductance. Now the strength of EMF induced in the coil will be given by E equals to minus d n phi b by dt. So putting the value of n phi b from here, which is L into I, we can rewrite as E equals to minus L into di by dt. And this equation gives the relation between the induced EMF, the self-inductance, and the rate of change of current in the coil.